Now we've talked about splitting functions and polynomials up using partial fractions, but what we have to do is understand what functions are and looking at some of the properties of it. So in this video here, I'm going to talk you through some of the properties associated with functions and some of the key things that we have to remember when we are working with them. And some of those are things to do with numbers they work upon and answers that we get out. Now the basic thing that we have to remember from when we introduced functions a couple of years ago at Higher is quite simply that functions are a rule. What it does is it assigns each member, so each number from a set A, to a unique element within a second set, which we're going to call B. So it takes one thing, does something to it, and you get a single answer, i.e. a unique answer out from a different set of numbers there. Now, this can be written in a variety of common ways. We've seen this way quite often, so y equals f of x. That's the most common way we've seen it. Another way of writing it is this sort of way here. So f colon x means the function with relation to x gives you y. And in this case, y is called the image of x in f. So i.e. what happens after you've done the rule to whatever value you've put in. So they can be written in either of these ways, but they all have the same basic premise of it's a rule, you do something for one set of numbers, you get an answer in the next set. What we have to be able to do is work with these. So what I'm going to do is I'm going to take this and I'm going to say, take the function f from x using the rule x squared. It's going to link each member of a set A, and I'm going to tell you that A goes from -2 to 2, so the whole numbers from there, to a member of set B, and I'm going to tell you the values of B go from 0 to 4. So what that means is I can take x squared, use that as my rule, apply it to any value in a set A, and I should get an answer in B that is between 0 and 4. So let's imagine I give you the value -2. If I plug that into my rule and I do -2 squared, well, -2 squared gives me 4. So what the rule does is it assigns that value, -2, to an answer of 4 using the rule. And this can be followed for any of the values. So if I take -1, do -1 squared, I assign that to the value of 1. If I then take 0 and do 0 squared, I assign that to the value of 0. And I can continue on with these elements here. If I take 1, do 1 squared, that gives me an answer of 1. But wait a second, this is where the question comes into play. Because if I look here, what this says is it's a rule assigning each member of set A to a unique element of set B. But this element here in B, the 1, is shared between two numbers which I've put into the function. But that is allowed. What this means here, from a definition, is that each value of A gets one and only one answer from the set of B. If I'd made a rule and what happened was when I put in 1, I ended up getting 2 answers for it, so I ended up getting 1 and, for example, 3, that wouldn't be assigned to a unique element in B because I could have 2 possible solutions to it. So I can assign one answer to more than 2 things that I've put in, to 2 or more things that I've put in. So I've assigned the 1 to an answer from when I input -1 and 1. And it's actually the same here because if I put 2 in and do 2 squared, I get 4. So again, I've taken the same answer in B, the 4, but I've assigned it to 2 different inputs. That is allowed. It can't go the other way around though. There's 3 key things we have to be able to identify and understand for each of the functions. That's domain, codomain, and range. Now the domain is the numbers the function acts upon. So in this case, my domain is the numbers I put in, which is given by my set A. So my domain in this case is -2, -1, 0, 1, and 2. The codomain is the set of numbers which give the answers. So it's the set of numbers I'm assigning it to, which contain all the numbers that gives me the solutions. So in this case, it's B. So in this case, my codomain is the value 0, 1, 2, 3, and 4. My range is the set of images of the function. Now what that means is my range is the solutions I will get from the function. So what values and answers could I get? Now in this case, I only got 3 possible answers. I got 0, I got 1, and I got 4. So in my range, those are the only numbers I include. Yes, my codomain has the 2 and the 3 in it, but I don't get a solution. They are not an image given by some value from A, so I don't include them in my range. Think of it that way. Range is the answers you get. Codomain is the bit where the answers could possibly lie, and domain is what we put into the function. Now, in this one, it's a very limited example. I've given you -2, -1, 0, 1, 2. So a couple of whole numbers, and I've given you a few whole numbers in the codomain to get an answer. But we've got more than just a couple of whole numbers. We need to understand how it works for every number that possibly exists. So what we have to do is we have to understand sets of numbers that we can either input or get as output from the functions. And in maths, there are several sets that do exist. And these are those. We've got our set n. That's the label given to it. And what this means is it's a set of natural numbers. Now, the natural numbers are everything from 1 up to infinity in the positive direction. So it's 1, 2, 3, 4, 100, 1,000,000, so on and so forth. We've then got the set w, and that's the set of whole numbers. Now, the difference between natural numbers and whole numbers is that whole numbers include the value of 0. Natural numbers don't. So essentially, whole numbers is our natural number set plus a 0. We've then got a third set, which is called z, and this is the set of integer values. Now again, you can look at that being, well, if I split it there and go up here, that's my set of whole numbers there, but I'm now also including negative numbers here, and that's where that differs from the whole number set. Now, a key thing to notice in each of these 3 sets of numbers is that I'm only looking at integer values. Each of these sets of numbers is only including integers. So I've got to somehow take into account other numbers I could get, because I can get decimal numbers, I can get surds, I can get specials. There's lots of other numbers we can do. So the next set of numbers I then expand out to is q, and that is a set of rational numbers. Now, that's any number that can be written as an exact value in surd format or some other way of writing it. So a fraction, for example. And what we're able to do is represent it in that manner, so we don't have to round it. So for example, square root of 2, I could have a half, I could have -1/8. These are all examples of rational numbers because I can write them as an exact value. We can then take that even further and go to R, which is a set of real numbers, basically every number in existence that does not include complex values, which is something we'll look at later in the course. So set of real numbers encompasses everything we've got at the moment. Now, I know that you're looking at it and saying, well, each of these numbers is subsets of others, why do I not just stick with real numbers? Well, using these helps me to limit the number of values just to make our calculations a bit easier. But if you think about it, if we take our n as being this central circle here, so my natural numbers, I can then draw another circle around it, representing my w, my whole numbers, because it encompasses the natural numbers, plus extra elements, i.e. just the 0. I can then expand that even further to make it out to be my z, my integers, because that includes all of my whole numbers and my natural numbers, but expands it out by including negatives as well. My set of rational numbers can then be taken beyond that as well. Now remember, rational numbers are numbers that can be written as an exact value. Integers are exact values, so that's included in it as well. Then I can expand it even further to take into account my full set of real numbers, so all the numbers in existence. So we can use those to our advantage, help us limit our range in our domain, make our calculations easier. One thing to remember though is quite often we have to put restrictions on these to have a suitable domain or range for our functions. Let me show you what I mean. Let's imagine I've got a function f of x equals square root of x. We've got to come up with a suitable domain and a range for this function here. Well, if I was to take this function f of x and sketch it, it would look something along the lines of that. Now the reason being, the only values for x I can input into here and actually get a solution out for is everything from 0 upwards. If I put a negative value of x in that, try and do the square root of a negative number, so square root of -4 for example, your calculator would say error. You can't do it. So you can't physically put anything from the negative values of x there. And in that same thought, any solution that I'm going to get from here is going to be above 0 as well. I'm not going to get any solutions down here where y is or f of x is a negative value. So I can use that in my thought for the domain and my range. So what I can then say is fine. So my domain, what that's going to be is all the numbers up here. Now that can include decimals, rationals, irrational numbers, etc. So I can say fine, so my domain is going to be the positive set of real numbers plus my value is 0, i.e. it's going to be everything above 0 and including it. Similarly, I can then look at it for my range, what answers I'm going to get, and I can say the same thing as well. It's going to be given every positive value within my real numbers, including our 0 value there. So that there is a suitable domain and range for this function, i.e. it tells me where the function exists and what answers I can get. Second example to show you is this one here. So f of x equals 1 over x minus 1. Now you're looking at that and thinking, great, I've got a function there where essentially my domain, I can plug in any value. So my domain could be the set of real numbers. But there is an issue. This is a fraction. And if the bottom of a fraction equals 0, you can't calculate it. So if I look at that, if x minus 1 equals 0, what that means is that I'm not going to get a solution. And for x minus 1 to be equal to 0, x has to be equal to 1. So in this case, my domain, yeah, it's going to be all the real numbers, but I'm going to take out the value of 1. So it can't be 1. My domain can't exist if I include the value of x being 1. I can then look at the same sort of thing for my range. So my range of values. So what possible solutions I can get. Now again, if I think about sketching this function here, what's going to happen is if I put x being a positive value and I get bigger and bigger and bigger for x, what's going to happen is the bottom, the denominator of the fraction, is going to absolutely dominate the top of it. And this is going to get closer and closer and closer to 0. So essentially, as I go off to infinity, my function is going to tend towards 0. Now, I've told you already, we can't have a value for x equal to 1. So there's my 1 there in x. It's going to look something like that. As it gets closer and closer to 1, this bottom part here is going to get smaller and smaller, so I'm going to end up with a value there. If I look on this side of the function, and I start to put a value in here for x as it tends towards a negative, this is going to be the same sort of logic as up here, but it's going to be a negative value. So it's going to tend towards 0 from below the x-axis. And as I get closer and closer to 1 from below it, that's going to be a negative value, so it's going to end up going towards negative infinity. So again, if I look, great, my values seem to be every single solution there. So it's going to be all the real numbers. However, you'll notice I'm getting closer and closer to 0 as I increase the magnitude or the size of x, but I'm never ever going to have something where I can divide 1 by a value and get 0. So for the range to exist, similarly to the domain, I'm going to have to take a value out. The difference being in this case though, is I'm going to have to take out 0 because that's the only solution I cannot get within that. Easy way to think about it. Domain, what do you put into the function? Range, what can you get out of the function? So what solutions can you possibly get? Now remember, 9 times out of 10 it's going to involve the different sets of numbers that we've talked about there. However, do bear in mind that like the very first example we did when I was talking to you about this, you could only have a limited set of numbers and you have to look at what solutions you get out of there and include only those within the range of your function. Bear all that in mind.